Potentiometer is an arrangement used for measurement of EMF of a cell or comparison of two cells or internal resistance of a cell. It consists of a uniform wire AC of few meters in length connected to a source emitter rheostat and a key K1 as shown in the figure. Very often, the wire is cut into small pieces. Very often, the wire AB is cut into small pieces held parallel and the sides are connected by metal piece. H, this is a metal piece. These are the metal pieces. The value of RH is selected for certain steady flow of current. Steady flow of current I in the circuit by closing the key K1. A voltmeter V is connected between A and J, where J is the jockey movable on the length of the wire AC. Movable on the length of the wire AC. Let I the current flow. Let I the flow of current from A to C. From A to C. And AJ is equal to L, the length of the wire. Hence potential drop V is equal to I into R dash, where R dash the resistance of the length of wire AJ, where R dash is equal to rho L by A, the resistance of wire of length AJ is equal to L. Again we can write V is equal to I R dash, that is I into rho L by A, or V is equal to some constant phi L, where phi is equal to I into rho by A. Rho is constant for material, constant for the specific resistance. Rho, the specific resistance of the wire is constant. I is steady current by adjustment of RH. For uniform wire, I is fixed or constant. Or V is proportional to L. So for a potentiometer, potential difference across a length is directly proportional to the length. Thus, for a potentiometer, the potential difference across a length is proportional to the length from the positive terminal A, from the positive terminal A of the source. Phi is known as the potential gradient, is the potential gradient. It is a constant for certain value of current, which is variable. It is a constant for certain value of current. While taking comparison or evaluation of any unknown quantities in a given cell, the arrangement is such that the arrangement of RH is assured so as the potential drop across SC is always more than the EMF of the cells to be compared. First application is comparison of EMF of two cells. The cells for which EMF is to compare are connected as shown in the figure E1, E2. The positive terminals are connected to A and the negative terminals are connected to a two-way key through a galvanometer. And when connected to cell E1, suppose there is some null point at J1, and when connected to other J2, the cells for which EMF is to be compared, E1, E2, are connected with positive terminals to A and the negative terminals are connected to jockey through galvanometer and a two-way key. H13 is connected and let AJ1 is equal to L1. The point on the wire for null deflection or null point for zero deflection in galvanometer. Then we can say that the EMF of this cell is equal to the potential drop across the wire of length AJ1, or we can apply the Kirchhoff's second rule or loop rule. By applying Kirchhoff's loop rule in A J1 G3 1 A. This is a circuit A J1 G3 1 A, or E1A, we can say G3 1 E1A. Hence E1 minus phi L1 is equal to 0, or E1 is equal to phi L1, where phi is the potential gradient of the arrangement. Again, as 2 3 are connected, now E2 is in the circuit and AJ2 is equal to L2, the point for which galvanometer deflection is 0. Galvanometer deflection is 0. Then applying Kirchhoff's second rule, then applying the loop rule, across A J2 G 32 E2 A. Here E2 minus phi L2 is 0, or E2 is equal to phi L2. From A and B, it is observed that E1 by E2 is equal to L1 by L2. If EMF of one of the cells is known, then other can be calculated. If either is known, the EMF of the other can be evaluated. Second application is internal resistance of a cell. Internal resistance of a cell. Here the cells in question E is connected to a resistance R with key K2. the EMF, the cell E for which small r is to be calculated is connected across A and J with a resistance R key K2 as shown in the figure. As shown in the figure. At first, K2 is open and AJ2 is L2, the point for zero deflection in galvanometer. That's why the EMF of cell, that is EMF of the cell E is equal to phi into L2 if AZ2 is L2. Again, when K2 is closed, there is flow of current across R. So the N terminals measure the potential difference of the cell. Potential difference of the cell, that is V is equal to phi into L1 if AJ1 is the length L1. Or that is, you can say that E by V. Again, V is equal to I dash, or V is equal to IR, where R is the resistance, and E is equal to I into R plus R. EMF is equal to R plus R. Or E by V is equal to phi L2 by phi L1, or IR by I into R plus R is equal to L2 by L1. So I into R plus R by IR is equal to L2 by L1. Or 1 plus R by R is equal to L2 by L1 minus 1 plus R by R is equal to by L1, or small r is equal to R into L2 by L1 minus 1. Thus, internal resistance of a cell can be obtained as R, L1, L2 are known. Thus, small r can be evaluated. The potentiometer has an advantage. The potentiometer has an advantage that it draws no current from the cell in question, that is E. Thus, internal resistance of the cell does not affect the arrangement